Hello students, Mr. Courtney here. In this video, we're going to be looking over stoichiometry. We'll be using stoichiometric ratios to perform conversions involving things like moles to moles, mass to mass, moles to volume, volumes to moles, moles to molecules, mass to molecules, all those. We're going to be doing all this using the balanced chemical equation. So stoichiometry involves the calculations of quantities in chemical equations. We're going to use the relationship between the reactants and products, or reactants and reactants, and then we use that to determine quantitative data. When we say quantitative data here, we're talking about numerical values. So we're not measuring it, we are going to calculate, we're not going to describe and those things. So we're going to calculate data. So let's start by looking at a balanced chemical equation. What information can we get from a balanced chemical equation? So we have here the reaction between carbon monoxide and oxygen to give us carbon dioxide. Now, if we talk in terms of representative particles, we have two molecules of carbon monoxide, one molecule of oxygen, and two molecules of carbon dioxide. And we get this from the stoichiometric ratio. That is the coefficients of our reactants and products. If we look in terms of moles, we have 2 moles of carbon monoxide, 1 mole of oxygen, and 2 moles of carbon dioxide. The mass, we take the formula mass of carbon dioxide, that's the mass of 1 mole. Since we have 2 moles, we're going to multiply it by 2, so that gives us 56. Oxygen is O2, so we just multiply its atomic mass by 2, that gives us 32. Carbon dioxide, we take the formula mass of carbon dioxide, which is approximately 44.0 grams, and multiply it by 2 because we have 2 moles. You have to remember that the formula mass is the mass of 1 mole. So if we have 2 moles, we need to multiply that mass by 2. Or whatever number of moles we have, we need to multiply by that number. In terms of atoms, each molecule of carbon monoxide has 2 atoms, 1 carbon and 1 oxygen. We multiply by the number of moles, so we have 2, or we say we multiply by the number of molecules. So 2 times 2 will give us the 4. We only have 2 and 1 mole, 1 molecule, so that gives us 2. We have 3 atoms times 2 molecules, that gives us 6 atoms. Now in terms of volume, we have 2 moles and we have 44.8 liters. 1 mole, 22.4 liters. 2 moles, 44.8 liters. So here we can develop a relationship between the volume of gas at STP, and STP means standard temperature and pressure. So we can develop a relationship between the volume of gas at STP. 1 mole of any gas at standard temperature and pressure is going to occupy 22.4 liters. Doesn't matter what the gas is, whether it's oxygen, carbon monoxide, carbon dioxide. If we have 1 mole of carbon monoxide, we take the 44.8 divide by 2. That would give us 22.4 liters also. To get the volume of 1 mole of carbon dioxide, we take our same 44.8 divided by 2. That gives us 22.4. So here we see 1 mole of any gas at standard temperature and pressure occupies 22.4 liters. So if we look back here, we see that mass and number of atoms are always conserved in a chemical equation. So that has to do with the law of conservation of mass. Because in a balanced chemical equation, we're going to have equal amounts of each atom on both sides. If we have equal amounts of each atom on both sides, then that means we're going to have equal masses on both sides. So the mass of our reactants must be equal to the mass of our products. So let's look at a mole-to-mole calculation. So we're going to use the mole ratios. We're going to use a relationship between moles of reactants and moles of products. And we're going to use what is called a mole ratio. To get that mole ratio, we're going to use the coefficients from our balanced equation. And these are what we will use as our conversion factors when we do dimensional analysis. All right, so let's look at this example. We have the reaction between nitrogen and hydrogen to give us ammonia. So let's see if we can develop relationships between the moles of reactants and moles of products, or between moles of reactants, and develop our mole ratios. So let's start with nitrogen to hydrogen. You see here we have 1 mole of nitrogen to 3 moles of hydrogen. Or we can say we have 3 moles of hydrogen to 1 mole of nitrogen. You can also say that we have 1 mole of nitrogen to 2 moles of ammonia, or 2 moles of ammonia to 1 mole of nitrogen. 3 moles of hydrogen to 2 moles of ammonia, or 2 moles of ammonia to 3 moles of hydrogen. So these are the conversion factors that we can develop from this one equation. Okay, so here we're asked how many moles of aluminum are needed to form 2.3 moles of aluminum oxide. So we have our balanced equation. Remember, that's the first step we always take. We realize that we need 4 moles of aluminum to react with 3 moles of oxygen, and that gives us 2 moles of aluminum oxide. So we look at what we're given in the equation. We're given 2.3 moles of aluminum oxide. We want to find moles of aluminum. So we start with what is given to us, which is a 2.3 moles of aluminum oxide. Then we look at our molar ratio in our balanced equation. What we want over what is given. So we have 4 moles of aluminum, 2 moles of aluminum oxide, sorry. And there we have our mole ratio, 4 moles of aluminum to 2 moles of aluminum oxide. We multiply 2.3 by 4 and then divide by 2. That will give us 4.6 moles of aluminum. So that's how many moles of aluminum are needed to give us 2.3 moles of aluminum oxide. In this example, we want the number of moles of oxygen that are required to react completely with 0.84 moles of aluminum. So we have our same balanced equation. We look at what we're given and what we want to find. We're given 0.84 moles of aluminum. We want to find how many moles of oxygen we have. So that means we're going to be using the mole ratio of oxygen to aluminum. But we start with what we're given, 0.84 moles. When I go to my balanced equation, I have 3 moles of oxygen to 4 moles of aluminum. So 3 moles of oxygen reacts with 4 moles of aluminum. And that we multiply 0.84 by 3, then divide by 4, and gives us our answer of 0.63 moles of oxygen. Here we ask to calculate the number of moles of aluminum oxide formed when 17.2 moles of oxygen reacts with aluminum. So we still have our same balance equation. We're given 17.2 moles of oxygen and we want to find moles of aluminum oxide. So we start with our 17.2 moles of oxygen. And since we want to go from moles of oxygen to moles of aluminum oxide, we need to use the mole ratio of aluminum oxide to oxygen. So it is always the mole ratio of what we want to find, or what is wanted, over what is given from the balance equation. So we're given 2 moles of aluminum oxide in the balance equation. We have 3 moles of oxygen also in that balanced equation. So 17.2 multiplied by 2, then you divide by 3, and that gives us 11.5 moles of aluminum oxide. Now, when we do experiments in the lab, we could never measure moles. We could calculate moles, but we measure grams. And we can use the relationship between grams and moles for each substance to convert grams to moles. So we're going to use that as a conversion factor. For example, in 1 mole of nitrogen, we say we have 28.02 grams. So in 1 mole of nitrogen, we have 28.20 grams. 28.0 grams. All right, let's look at the steps to a stoichiometry problem when we go from mass to mass. First, we're going to write the balanced equation, just like we've been doing when we were going from moles to moles. We write the balanced equation. Then we're going to convert whatever mass we're given to. Whatever mass we're given, we're going to convert that to moles. And to do that, we divide by our formula mass. Then we're going to convert moles of the first substance to moles of the second substance. And we do that by using the mole ratio from the balance equation. That is a coefficient from the balance equation. And as I said before, the mole ratio is in terms of moles of what is wanted. So our unknown amount from what is given, and our moles of what is given. So that's how we form our mole ratio. And then we're going to convert our moles of the second substance into grams by multiplying by that formula mass. Okay, so let's look at this example. We are asked to calculate number of grams of solid sodium oxide that will be produced when 115 grams of solid sodium react with excess oxygen. So first step, write your balanced equation. So we have 4 moles of sodium reacting with 1 mole of oxygen to give us 2 moles of sodium oxide. Then we identify what we're given and what we want to find. We're given 115 grams of sodium. We want to find how many grams of sodium oxide that will produce. So first step, we go from grams of sodium to moles of sodium. We know in 1 mole of sodium we have approximately 23.0 grams. Now that we've gotten our grams of sodium, we will go to our balanced equation to find our mole ratio, to go from moles of sodium to moles of sodium oxide. So we're going to use the ratio of what we want to what is given from the balanced equation. So from the balanced equation, we have 2 moles of sodium oxide to 4 moles of sodium. Now that we have moles of sodium oxide, we're going to multiply by the formula mass of sodium oxide. That is how many grams we have in 1 mole to give us our mass. Once we've done that, we're going to get a mass of 155 grams of sodium oxide. So how many grams of oxygen are required to burn 13.0 grams of ethane? So we have 13.0 grams and we want to find how many grams of oxygen. So again, we have our balanced equation. We identify what we're given. We're given 13.0 grams of ethane to find how many grams of oxygen it needs to react. So we start with our grams of ethane and we go to moles of ethane. Then we go from moles of ethane to moles of oxygen. Moles of what is wanted divided by moles of what is given from our balanced equation. That's our mole ratio. We have 5 moles of oxygen to 2 moles of ethane. Then we multiply by the formula mass or the molecular mass of oxygen gas, which is 32. And then we in 1 mole, 32 grams in 1 mole. Now, some of you may be tempted to multiply by 5. Do not do that. All you're doing is multiply by your formula mass, not how many molecules or how many moles of it you have, just by the formula mass. And that gives us an answer of 40.0 grams. And that's grams of oxygen. Alright, so we're asking how many grams of carbon dioxide and grams of water are produced when 13.0 grams of ethane reacts with an excess amount of oxygen. So that means we have to find how many grams of carbon dioxide and how many grams of oxygen are produced from that same 13 grams of ethane. So we start with our calculations for carbon dioxide. We have our balanced equation. We start with 13 grams and we want to find how many grams of carbon dioxide. So we go to moles of ethane. We've done this already. Now we want carbon dioxide. So the mole ratio of carbon dioxide to ethane, it's 4 moles of carbon dioxide to 2 moles of ethane. Then we multiply by the formula mass of carbon dioxide, which is just CO2, not 4CO2. So remember that. How many grams we have in 1 mole, and that gives us our mass of carbon dioxide, which is 44.0. Now to do our calculate for water. We start with our 13 grams of ethane converted to moles of ethane. Now we want water from the balanced equation. Mole ratio of water to ethane, it's 2 to 2 or a 1 to 1. Then we multiply by the formula mass of water. That's how many grams we have in 1 mole, and that gives us our answer of 9.00 grams of water. So this is pretty much similar to the first one you did, except that your mole ratios will change. It's not no longer carbon dioxide to ethane, it's water to ethane, and then you multiply by the molar mass of water. So now we're asked to use the answers from A and B to show that this equation obeys the law of conservation of mass. And for the law of conservation of mass to be obeyed, the mass of our products must be equal to the mass of our reactants. So let's find the mass of reactants. We started with 13 grams of ethane, and we know it reacted with 40.0 grams of oxygen because we calculated that. So that gives us a total of 53.0 grams. Now the mass of our products, 44 grams of carbon dioxide with 9 grams of water, total of 53.0 grams. So here we see that the mass of the reactants is equal to the mass of the products. That tells us the law of conservation of mass is obeyed. This one asks us how many grams of tin fluoride can be made by reacting 7.42 by 10 to the 24 molecules of hydrogen fluoride or hydrofluoric acid with tin. So we write our balanced equation, first step, and we identify what is given to us. We're given 7.42 by 10 to the 24 molecules of hydrofluoric acid, and we want to find how many grams of tin. So we're going from molecules to grams. So we have molecules. How do we go from molecules to moles? So that's the first thing we need to do. Since we have this balanced equation, and the balanced equation gives us a mole ratio, then we need to convert our molecules to moles of hydrogen fluoride or hydrofluoric acid. And we're going to do that by dividing by Avogadro's number, because we know in 1 mole of any substance, these are the number of particles we have. So to convert our particles or molecules to moles, we divide by Avogadro's number. Once we have that, then we go from moles of hydrofluoric acid to moles of tin fluoride using our stoichiometric ratio. So we have 1 mole of tin fluoride to 2 moles of hydrofluoric acid. Then we multiply the moles of tin fluoride by its formula mass. That's how many grams in 1 mole to give us our answer. And that gives us 966 grams of tin fluoride. Part B. How many liters of hydrogen gas at STP, standard temperature and pressure, are produced by reacting 23.4 grams of tin with hydrofluoric acid? So we have our balanced equation. So that means we're going from grams of tin to liters of hydrogen. So we start with our grams of tin, that's what's given. We're always going to convert grams to moles. Whatever we're given, we're going to convert it to moles. So to get moles of tin, we do in 1 mole of tin we have 118.7 grams. Now that we have moles of tin, we need to go from moles of tin to moles of hydrogen gas. So we look at the ratio, the mole ratio of hydrogen gas to tin. And it's a 1 mole to 1 mole, so a 1-to-1 ratio. Then we multiply by 22.4 liters. Remember we said at the beginning, that's how many liters we have in 1 mole. So we multiply by 24 liters of hydrogen in 1 mole of hydrogen. And that will give us our number of, our volume of hydrogen gas produced, which is 4.42 liters. Here we ask how many liters of hydrofluoric acid are needed to produce 1.42 liters of hydrogen. So we have our same balanced equation. Now we have liters of hydrogen. That's how many liters of hydrogen were produced. We want to find how many liters of hydrofluoric or hydrogen fluoride here. We're using it as a gas though. Hydrogen fluoride is required to produce it. So we started our 14.2 liters of hydrogen, converted to moles of hydrogen. We go to our mole ratio of hydrogen fluoride to hydrogen. So that's 2 to 1. So for every 2 moles of hydrogen fluoride, we produce 1 mole of hydrogen gas. Then we multiply by, and since we want liters, so now that we have moles, we need to multiply by 22.4 liters, because that's how many liters we have in 1 mole. And you have to remember that's the liters per mole. 22.4 liters per mole is for any gas. 1 mole of any gas at standard temperature and pressure occupies 22.4 liters, a volume of 22.4 liters. And that will give us our answer of 28.4 liters of hydrogen fluoride. Now, when we talk about volume to volume, as we've seen, the coefficients can indicate different things. For especially volume to volume, it will tell us the relative number of moles and the relative volumes of interacting gases. Let's see how that applies in an equation or in a problem. So we're asked, how many molecules of hydrogen are produced by the reaction of tin with 80.0 liters of hydrogen fluoride at STP? And that STP is important because it indicates to us certain things. And we'll refresh your memory on this in a bit. So we look at what we're given. We're given 80.0 liters of hydrogen fluoride, and we want to find how many molecules of hydrogen gas. So we start with our liters of hydrogen fluoride. As I said before, convert your liters, whatever you're given, convert it to moles. And we know that in 1 mole of any gas, we have 22.4 liters. So that gives us moles of hydrogen fluoride here. Then we look at our balanced equation. What is the molar ratio of hydrogen to hydrogen fluoride? So 1 to 2. And since we want molecules, we have to go from moles to molecules. We have 6.02 by 10 to the 23rd molecules in 1 mole, or 1 mole contains 6.02 by 10 to the 23rd molecules. So we multiply by Avogadro's number here, and that would give us our value. And that gives us a value of 1.08 times 10 to the 24 molecules of hydrogen. So here we just changed it up a bit different. We didn't start with grams, and we didn't end with grams, or we didn't start with moles to end with grams. We started with liters to end with molecules, but the principle still remains the same. Whatever you're given, convert it to moles of the substance, and use your mole ratio to get moles of the second substance. Once you have moles of the second substance, you can go to whatever unit you want, whether you want to go to molecules, you want to go to grams, or you want to go to volume. You can do that all from determining the moles of the substance you used. Alright, so this takes us to the end of this video. Until the next time, I'm out. Blessings.